All right, so the last thing I really need to talk about equilibrium is this thing called Le Chatelier's principle. Le Chatelier's principle has to do, it basically is a principle that functions under a very specific circumstance. So here we go. So imagine that we let a reaction happen and it reaches equilibrium. So it's already at equilibrium. And now I'm going to mess with it. And I'm going to not, screw with the equilibrium so it's no longer at equilibrium anymore. That's the situation we're talking about. So Le Chatelier's principle specifically has to do with a reaction already at equilibrium, and then I monkey with it. What happens now? So one thing you have to realize before going into this, the system was already at equilibrium. I'm monkeying with it. So we've got to think about all we really have to figure out is, which way did I throw the system? Did I throw the system so that it has more products than it should have at equilibrium? Or should it have more reactants? Or does it have more reactants than it should have at equilibrium? So basically, the Chatelier's principle says that the system is going to try to get back to equilibrium. No matter which way you shift it, it's going to try to go back, even if that means running backwards, running in the reverse direction to get back to equilibrium. So remember, equilibrium for any given reaction is a specific ratio of products to reactants. So keep that in mind. So all you have to think about is, which way did I screw up the equilibrium? Did I shift it so that it now has, if it now has too much reactant, it's going to run forward to get rid of the reactant and make product. If it now has too much product, it's going to run backwards. Let me draw this all out. I think that'll make much more sense. I'm just going to do my generic A, B, C, D thing. And remember, K equals, so if it's J, K, L, oops, that's not an L. L, M, so C to the L, D to the M, A to the J, and B to the K. Okay. So, remember, products of reactants. So if I now have too much product, the reaction is going to run backwards, because what that'll do is it'll get rid of the product, make reaction, it'll bring this down and this up, so K will go back to where it's supposed to go. So in other words, too much product means my value is, the ratio is now too high, and it's got to go back to equal whatever K should be. The other situation is if I have too much reactant, in which case it's going to go forward to get rid of the reactant and make product and get back to K. Okay, so there's two outcomes. Oops, which I've really just covered, but I'll put it in print for those of you for whom that is easier. There we go. So the system shifts right to consume reactant and produce more product, or the system shifts left, reverse reaction, or reverse direction to consumes product and produces more reactant. Okay, so Le Chatelier's principle states that if stress is applied to the system, so this is kind of the shortcut. Le Chatelier's principle is that if stress is applied to the system at equilibrium, the system will readjust to reduce the stress. So the system was already comfortable at equilibrium. I stressed it. It's going to try and get rid of the stress. There's four types of change. Changing the concentration of something, changing the temperature, changing the pressure, and adding a catalyst. So let's talk about each of these in turn. Concentration change. Okay. I could either add a product, add a reactant, take away a product, take away a reactant. So if a reactant or product is added, the system moves in a direction that consumes whatever I added. So A plus B produces C plus D, right? If I add extra A in there, so I increase how much A is in the system, which way does the system go? it goes to the right because I've unbalanced it. I've given it too much reactant. It wants to get rid of the extra reactant. The system goes right. If I add C, the system goes left to get rid of it. The converse of this is just if I were to remove B, right? Now the system has less B than it should and it needs more. It's going to go left. It's going to shift left to fill in the hole that I left, right? Now I'm not saying I'm removing all of B. I'm just removing some of it. But remember, the system before I mess with it is at equilibrium. It's at perfect balance. So if I remove D, then the system is going to shift right to replace it. So that's really all you got to know with equilibrium. It's going to shift towards anything you remove and away from anything that you add. Okay. So here we go. If we add excess N, if I add excess N2, if I add nitrogen, the system's going to shift right to get rid of the extra N2, assuming it was already at equilibrium. If I add excess ammonia, it's going to shift left to get rid of it. If I remove hydrogen, it's going to shift left to replace it. And if I remove some NH3, it's going to shift right to replace it. Just think about it in those terms. It's going to try to remove any extra you add and fill in anything you take away. Temperature. Temperature is tricky, but you can think about it in sort of similar terms as you think about the concentration changes. And so, temperature affects the equilibrium of the system. So one thing to know is that changing the concentrations disrupted where the system was by knocking it off of Q or off of K. Changing the temperature actually changes K. It actually affects the value of K. So it makes K bigger or smaller. So, and you can kind of figure out whether we're making K bigger or smaller. So only temperature. Temperature is the only thing that affects K. Just like density for a given substance is a set value at any temperature, K is a set value for any reaction at any given temperature, or at a specific temperature. So, reactions are going to behave differently depending on whether they're exothermic or endothermic. This is probably getting down the rabbit hole and starting to seem a little overwhelming. However, we can consider heat to be a product or a reactant. So, think about an exothermic reaction. If it's an exothermic reaction, is heat, so let's do A, B, C, and D. If it's an exothermic reaction, is heat a product or a reactant? Exo means heat is coming out. It means heat is produced. We can think of, for exothermic reactions, you can think of heat as a product. You might see where I'm going with this now. If it's endothermic, you have to put heat in. Heat is a reactant. Now we just use the same rules as before. So for an exothermic reaction, like this one, we have, H2, F2, and then HF, plus heat coming out. And you know it's heat coming out because it's exothermic. If I increase the temperature, it's the same as increasing a product, as adding a product. Which way will the system shift? The system will shift to the left to reduce the excess heat. It'll shift away from what we're adding. If I took away heat by lowering the temperature, it's going to want to replace it, and it will shift to the right. Okay. But going back to where it shifts to the left, shifting to the left means K has to go down. Because remember, left is lower K, right is higher K. Only temperature's changing K, though. Okay? So if we decrease the temperature, it's going to the right. K is increased because it's shifting to the right. Endothermic reactions have the opposite effect. Right? I'm increasing the amount of heat present. If I increase temperature, which way is it going to go? I'm adding a reactant. It's going to shift to the right to remove it. Right? that means K is going to go up. K is increased because it's going to the right. Right means K is up. Only for temperature, though. Nothing else changes K. Just remember that. Only temperature changes change K. If we decrease the temperature, I'm taking away a reactant. I'm taking away a reactant. We need to fill it in. We shift to the left, right? And K is going to go down. Okay. Pressure. Okay. This is easy. Pressure changes only affect equilibrium when we have a gas involved. And this is the same idea. We're going to create a stress, and we want to remove it. We want to relieve it. So consider a reaction like this. The thing to note, specifically look at the gas. Note how many moles of gas are on the reactant side and how many on the product side. So we have a total of 2 moles of hydrogen and 1 mole of oxygen. That's 3 moles of gas on the reactants becomes 2 moles of gas on the products. So this reaction goes from 3 moles of gas to 2 moles of gas. So every time the reaction moves forward, the total amount of gas goes down. So pressure changes result from volume changes. So if I start to increase the pressure, I'm going to have to do what to the volume? I have to decrease it, right? So, So this is important to know. Adding an inert gas doesn't change anything. I have to be changing the volume. So if I decrease the volume and increase the pressure, right, I'm smashing everything down. How can the system relieve that? It can relieve it by reducing the amount of gas present in the system. And it can do that by moving forward. It can move to the right. So every time it goes to the right, as it goes to the right, it takes, 3 molecules and makes 2. So it's actually producing the total amount of gas, right? So shift to the right to reduce the amount of gas molecules. If we increase the volume, it's going to want to fill that up, and it's going to shift left. So you just have to pay attention to how many moles of gas are on each side of the reaction, right? So if you smash the system down, increasing the pressure, it's going to shift to the side that has the fewest moles of gas. If you increase the volume and bring the pressure down, give it lots of room to breathe, it's going to expand by going to the side that has the most moles of gas. So this one, take a look at this. So first thing to consider, which side has more moles of gas? Reactant side has 3, product side has 5, right? So 2 here, 1 here is 3. So I'm going to write that down, 3 moles. Up here we have 5, right? 4 here, 1 here. So increasing the pressure by decreasing the volume, I smash it down, it's going to go which way? It's going to go to the side with the least gas, it's going to go to the left. Now this does not change K, right? This doesn't change K. K doesn't change unless the temperature changes. We're knocking it off of K, and then it's got to get back. Okay, decreasing the pressure by increasing the volume, it's going to shift to the right. There it is. And the last thing I have to say on this chapter is adding a catalyst does nothing to the equilibrium of the system. It doesn't do anything. Adding a catalyst has no effect on the equilibrium position. It just gets there faster, right? So concentrations, pressure, temperature, these all change the equilibrium. It'll affect and screw with the equilibrium. Adding a catalyst doesn't change the equilibrium. It doesn't change anything about it. It just gets there faster. That's it. That's all a catalyst does. It makes you get there faster by providing a lower activation energy. Okay. Phew.